We understand that mole is defined in chemistry as the quantity of substance basically carried on from mass, right? So mole is defined as mass in grams divided by the molecular mass of the system. Another way of looking at this would be visualizing this through Avogadro's constant, which is AV, right? So Avogadro's constant says that the number of atoms in any 1 mole of sample will always be 6.02 into 10 raised to power 23 atoms, right? So this is atoms per mole. So another formula for mole generally is written down as moles equals to number of atoms of that sample divided by the Avogadro's number, which is 6.02 into 10 raised to power 23 atoms per mole, right? So moles can also be found by this method. Then we have the second point that we've already discussed in terms of the number of atoms, that what Avogadro's number would mean. So for example, if we had to calculate the moles of carbon dioxide, a carbon dioxide gas has a molecular mass of 44. So 44 grams of CO2 will have Avogadro's number of atoms inside it. Similarly, if we were looking at sodium, that has a molecular mass of 23. So 23 grams of sodium would have the same number of atoms as 1 mole of Avogadro's atoms, right? Now we move towards the equation of state. First, the idea starts from O levels, which is PV equals to T, where T is the thermodynamic temperature. When we talk about the thermodynamic temperature, he is actually referring to the Kelvin scale, and is not talking about the degree centigrade or degree Fahrenheit. So, starting with this basic idea, what is PV equals to T? So, PV proportional to T. This equation can be broken down into three more parts, right? So, we have pressure being inversely proportional to volume, pressure being directly proportional to temperature, and then volume being directly proportional to temperature. So these are three equations that actually follow out from this system, from these equations. And it is assumed that since temperature is missing in the first system, the temperature is constant in this setup. Similarly, on the second hand side, we are talking about pressure and temperature, then most definitely volume is assumed to be constant. In third stage, we have pressure missing in the equation, so pressure will be assumed to be constant in this situation. Now, we observe the first law, we observe the first point, which basically is known as Boyle's law. So this is Boyle's law. You must have done this in O levels as well. So pressure and volume, they are inversely proportional, and the graph goes something like this. And we had an equation that was P1 V1 equals to P2 V2. Where does that equation actually come from, mathematically speaking? So he says that if volume is taken to that side, we're left with an equation that is PV equals to a constant K. So if you increase the value of P, V decreases, but the product of the values will give you the same answer. So pick up two values from the graph randomly, but be advised that these coordinates should be picked out from the line of the graph. So let's say this is P2, this is P1, and this is V2, and this is V1. We are keeping the nomenclature same. So as the product is supposed to be same, this basically boils down to the idea that P1 V1 should be equal to P2 V2. Since both of the products are supposed to be equal to a constant K, since both are going to give you the same value of constant, hence the situation arises P1 V1 equals to P2 V2. Then we move towards the idea of pressure being proportional to temperature. The theoretical understanding remains the same. How increasing temperature increases the pressure. So we know that increasing temperature causes an increase in kinetic energy. And if the kinetic energy increases, the speed of the molecules increases. And if the molecule speed increases, we know that the change of momentum increases. And we know that force is equal to rate of change of momentum. So if momentum increases, the force increases. And we know that pressure universally is force divided by area. So if we increase the force, the pressure increases. So that is the whole thought process for the pressure and temperature thing. And similarly for volume and temperature as well, if you increase the temperature, similar things happen over here as well. So the internal pressure increases and it pushes back onto the, or causes expansion. So the volume eventually increases for the gas, right? And the pressure stays constant throughout the process. How it happens is that it happens momentarily and in stages. Let's say if this is our syringe, the pressure of gas inside the cylinder, then there is an atmospheric pressure on the outside of the cylinder. So when you provide heat to the system, because we're exploring temperature and volume, the pressure of gas inside the container increases momentarily for a very short amount of time. And as it increases, because of the temperature, as we've already explored, the gas molecules apply a force from the inside, which is a bit greater than the external force due to the atmosphere. So the piston or the syringe moves slightly forward. Now, when it moves to the new position, now since volume has increased, the pressure drops due to the first Boyle's law. Now, when the pressure drops, they become equal again. Now, when they become equal, the syringe is seen to be holding this position. Now, since you're continuously providing the heat, this process goes on and on, but in very small steps. So small, in fact, that it looks like that the pressure on an average stays the same. The moment pressure inside the gas increases, it pushes the piston forward, and it does so until the pressure inside and outside becomes equal again, right? Okay, so we have a formula for Boyle's law, which is P1 V1 equals to P2 V2. So the first point asks us to explore all of these three properties. What we've done here is just a reminder of what we've already done in O levels. And we ask in the second point to recall the equation of PV equals to nRT and PV equals to nKT, right? So let's explore this equation. You must have done this in chemistry already. So PV equals nRT. Basically, this equation actually does come from the idea that PV equals to T, or PV is proportional to T. So let's start from that point. So PV proportional to T. Now in mathematics, if you want to convert the proportionality into inequality, we come to this point. So T will be in place as it is. PV over here are in place, but we need to add a constant of equation that is going to be K. Now we assume generally that throughout the process, the mass of gas remains constant. Now, why do we have to say this? Because we want to make sure that there is no leakage of the gas. Because if there was leakage, if the gas molecules are escaping, then it defeats the purpose. It defeats the idea because gas molecules have to collide with the surface of the container to create pressure. If the gas molecules are escaping, then the pressure will not maintain this relationship anymore. So to keep this mass constant, we introduce the idea of moles, right? We've introduced the idea of moles, so N represent moles, and still there is one constant missing for the ideal gases, which is the universal gas constant, which actually binds this equation together in this mathematical expression. Of course, the value of R for different gases under extreme circumstances, for example, at very high temperatures and very high pressures, most definitely the value of R will be different for other gases, which is what we explore at higher levels, right? But at this point, we're going to explore that R is going to remain the same. Okay. So the next idea is, if we are interested in the mass of the gas, then why are we representing it in moles? Basically, the problem is that mass of each individual atom is insignificant, and it is not possible to include all of them in this equation. So talking about all the atoms at the same time looks more plausible. That is why we have involved moles in place of mass, so that we can talk about it in terms of atoms and their collisions instead of the whole entity as a single unit, right? So pressure is P. Pressure is supposed to be in pascals. V is volume. Be advised, volume is supposed to be in meter cube. That is your job to convert this into meter cube. This is moles. And this is the universal gas constant, which is 8.31. And this is our thermodynamic temperature, which will be measured in kelvins as usual. And we know that the equation to convert degree centigrade to Kelvin is temperature in Kelvin is equal to 273.15 plus temperature in degree centigrade. Okay. So this is the equation that we should be familiar with and how to use this equation. We're going to solve a question to understand how to use this equation. And then the second part of the same item of the syllabus is to get familiar with this representation, that is PV equals to NKT. So what basically happens is that we're going to rewrite this formula as PV equals to nRT. And in place of moles, we're going to represent the formula for moles, which was with number of atoms. So moles is number of atoms of the gas divided by the Avogadro's number of 1 mole atom multiplied by R multiplied by T, right? So simply rewriting this in this format, that now we're going to place this Na not in the division of N but in the division of R. We're just dividing it like this. So this section, which is R by Na, is referred as the constant K in the system, in the syllabus. So the equation actually comes down to PV equals to capital NKT. Now over here, this K is universally known as the Boltzmann constant. And most definitely it has a value which is 1.38 into 10 raised to the power minus 23, right? And if we look at this, so this is actually 8.31, which was the value of R, divided by the Avogadro's constant, which is 6.02 into 10 to the power 23. So you can see where this negative 23 is coming from. It actually has to go up. Okay. All right. So we understand how this is being represented. We understand what the Boltzmann constant is actually equal to, which is equal to R over Avogadro's constant. And we have successfully completed the second part of the syllabus. Again, the third part is also covered, as he says that the Boltzmann constant is given as R over Na. Since R is also a constant, Na is also a constant, so this becomes the Boltzmann constant, the ratio, right? Okay. So now we move towards the idea of solving a question. He mentions some standard situations for the containers A and B, and it tells us that the pressure in the container is exactly the same. He wants us to find out the total moles in the container or the system. Okay. We'll mention one more point, I think, over here, that the tube has a negligible volume. Why does he have to say this? So that the total volume or the individual volumes that are given to us can be used as it is, as given in the question. We don't have to add this volume in the question. Otherwise, it will be a different situation, where generally he will assume situations to be something similar. So we know that PV is equal to nRT. Since we are required to find moles, I will make moles the subject of the formula and land in this equation, which is going to be PV divided by RT equals to N. So NA will be representing the moles of container A and NB will be representing the moles of container B. Since we are finding the total number of moles, that would be number of moles of A into number of moles of B. So using this equation, again, putting in the values that are already given in the question. So PV divided by RT, right? So pressure is given to us as 2.3 power 5. Don't forget to put in the powers. So 2.3 into 10 raised to the power 5. Then we have volume. Now notice that A has a volume of 3.1 power 3. So one more thing, 3.1 10 raised to the power 3, it has to be divided by 100 cube. Why? So that we can convert this from centimeter cube to meter cube. And then divide this with R, which is 8.31, and temperature is 17 degrees centigrade but has to be converted into Kelvin, so this will be added with 273. This is the moles for the first scenario. This moles for the second container would exactly follow the same formula but with different values. The pressure coincidentally is exactly the same because they're connected with a single pipe, but the volume is different in this container. So again, 4.6 power 3 will be divided by 100 cube to convert this into meter cube, right? And then we have 8.31 into 30 degrees plus 273, right? So if you solve it individually, I'm going to write down these answers so that you can confirm them. So this is 0.296 plus the other one will be 0.420 If you add them both together, this will be 0.716. So we understand how to use the PV equals to state equation, nRT. The next situation is about ideal gases and the kinetic theory of gases. First, we need to understand what are the basic kinetic model of matter for the ideal gases, right? So what we're assuming is that the particles are in constant random motion, right? The combined volume of the particles are negligible. What do we mean by this point? It means that in a container of gas, be that our own room, be that a syringe, if we individually could collect each and every atom in that space and confine them as much as possible that they are touching each other to a very small space, the space that they occupy will be incomparable, will be negligible, will be near to zero as compared to the space that they can actually occupy. So basically, what they're trying to say in this point indirectly is that there is a vast gap between the atoms of the gas and there are no forces of attraction between them. Because if there were forces of attraction, they would eventually become a liquid, but it's not, right? Particles have no forces on each other, which is again another, you can say, guarantee from this kinetic model of matter that there are no forces between them because they have a very large distance between them. Any collisions between them are perfectly elastic, which means that they can exchange energy with each other without losing energy to the system or due to the collision. Like in generally what we experience in real life, if two objects are colliding, they might lose energy in terms of deformation, in terms of sound, in terms of thermal energy. But in this case, it's not. They're not losing any energy between collisions and due to the collisions. The average kinetic energy of the particles is proportional to the temperature. This is what the highlight of the chapter is about. This is what we have to conclude, and this is what we have to basically derive and conclude our whole chapter on this fifth point. So we're going to go through some derivations from point 2, 3, and then eventually landing to point number 4. Let's start with those derivations. In the first part, it asks me to find out a relationship that looks like this, that eventually comes down to the fact that pressure and volume are going to be linked like this. So let's see how that system actually comes by. So the proof starts in a similar direction or in a similar fashion, that there is a cube or an occupied space, most definitely, that has uniform length from both sides. So length L and length L. And if you wanted to find the volume of this cube, that would be L cube simply. And we have a singular atom of gas. Of course, there are other atoms of gases, but we are only considering just one. So it moves towards this side, collides with the wall, and then comes back, right? So first, we observe the change in momentum. So the change in momentum goes something like this. Now, the speed of this particle, c, is the speed of the atom. Do not confuse this with the speed of light. It is only for this one, right? So, and m is the mass of the atom. So if we wanted to find out the change in momentum, because we ultimately want to find the force, because force divided by area is pressure. So the change in momentum should be final momentum minus initial momentum. We know that it was moving towards the left side, right? So that will be a negative velocity. And when it collides and goes back to the right side, it will be a positive velocity. So final velocity is mass multiplied by positive v, because it collides and goes to the right, minus mass multiplied by negative velocity, because initially it was moving towards the left side. So this comes out as mv plus mv. Sorry, I'm writing v. I should have written down c in this place. Okay. So this is c and c and c. So this becomes 2mc. So the total change in momentum is 2mc, right? Now, the second step would be to find out the time taken for the process. How does it change? So the molecule we are assuming is starting from this one edge, covering the whole distance and then colliding to come back. So we use the simple formula for speed is equal to distance over time. Now we know that the speed of the gas atom is c and the distance is going to be 2L. Once the L will be considered for incoming distance and then going away. And this is being divided by T. So we arrange T, so the T is equal to 2L divided by C. So this will be the time taken for the process or for this change of momentum, right? Then we use Newton's second law to find out the force which actually comes out from this idea, that rate of change of momentum. So we know that the momentum is 2mc. We know that the time is 2L by c. Replacing these values gives us 2mc divided by 2L divided by c. Now we can see that there are some things that are going to be cancelled. So 2 cancels out and c goes up. So we are left with mc squared divided by L, right? So this is the force that is being exerted on the surface of this cube, right? So then we go towards the idea of pressure. Now we know that pressure is equal to force over area. We have found out that the force is mc squared over L, so this will be replaced as mc squared divided by L divided by the cross-sectional area of one face of the cube will actually be, this side is L, this side is also L. The total area on which the molecule is colliding will be L squared. So this is being divided by L squared. Simple algebra leads to the idea that L is going to come down, right? So this will be mc squared divided by L cube. Okay. Now we go to the next step where we understand that this is the pressure due to just one molecule, right? This is the pressure of one molecule. What if we had to consider all the molecules? So let's involve a new variable that represents the number of atoms inside the container. So if we had to find out the total pressure now, that would simply be mc squared divided by L cube multiplied by this number n, because this was being generated by one atom. So if it had 1,000, 2,000, 1 million, or 2 million atoms, then those atoms would have to be multiplied by this. So we come down to the formula that is nm c squared divided by L cube, right? The next step would be to introduce this pressure being normalized in 3 dimensions, because the molecule could be moving in x-axis, could be moving along y-axis, and could be moving along z-axis. It could have all 3 components. So to normalize this, or to reduce its value along 3 axes, we are going to reduce its pressure or multiply a factor of 1 by 3. So the actual pressure comes down to 1 over 3 nm c squared divided by L cube, right? One more addition of variable over here would be the root mean square speed. Basically, we are trying to avoid the idea that the molecule could be moving towards the right side, could be moving towards the left side. What we are trying to do is, whatever velocity may be, we will take a square of it, right? And then we will take an under root of that value to balance out that square. So we're just trying to remove the negative sign due to the momentum's idea, and then trying to come back to the same value that was first squared. We take the under root to bring it back. To represent this root mean square, the variable that is used is going to look something like this. So bracket with c square, bracket close. Okay. So this will be pressure is equal to 1 over 3 nm with the root square symbol divided by L cube. Now, if we go back, we can remember that L cube was basically our volume, right? So if we replace L cube as V and then take this V over there, we are left with the equation that is PV equals to 1 over, sorry, this is going to be 1 over 3 nm c squared. And the main point of this equation, or the main understanding of this equation, is basically that this left-hand side PV is actually a macroscopic idea. And the right-hand side of the equation is actually microscopic idea or representation. What do we mean by the macroscopic? Macroscopic would mean values and properties on a larger scale, right? So what is the pressure of the gas? What is the volume of the full gas that is occupied inside the cylinder? So you're considering the whole system. where on this side, you are only considering and only talking about atoms. What atoms are actually contributing to the pressure and volume of the gas. So if you know about just one atom and the number of atoms, you can predict the rest of the behavior of the gas. So microscopic, because we're looking at atoms specifically, and macroscopic, so we are observing the properties on a larger scale. What's actually happening to the gas at the end of the day. So this is how the equation actually, this is why the equation is important, because it associates two properties or two sides of the same idea together. So we have done this point number 2 as well, and we understand that the RMS speed will be taken as the under root, right? So we understand point number 3 as well. Now we're going to reverse point number 4, in which he wants us to actually combine these two equations and see what comes out, right? Okay. So basically, going back as a revision, as one of the points that we have been talking about from a very long time in this temperature and thermodynamic system, now is the time to actually prove it. The idea was that the temperature of the system was proportional to the kinetic energy of the atoms. Now we're going to prove it in this stage, in the next proof that we have. And then we're going to look at a proof of values as well. So by this time, what we have found is that PV is equal to 1 over 3, right? So 1 over 3 nm root mean square speed. And we have another equation that is PV equals to nkt. And now we got the K, where we know that K is equal to R over NA, the Avogadro's constant, right? So since both of them are equal to PV, we can equate both of the equations, right? So we are left with, let's call this equation A and let's call this equation B. So equating A and B by comparing PV, we get 1 over 3 nmc square equals to nkt. Now notice that n was actually the number of atoms in the previous case as well. And over here as well, the n will be cancelled out. And let's take that 3 over there. So we have m c square is equal to 3 kt. Now the only thing left or missing in this equation, because this seems very similar to the kinetic energy formula, which is half mv squared. So the only factor missing in this system is the addition of 1 over 2. So mathematically speaking, what we can do is multiply both sides, left-hand side and right-hand side, with a factor of 1 by 2. So this becomes something similar that we've already done. And multiplying 1 over 2 over here will actually add a factor of 3 by 2. Sorry, not 3 by 2, but 1 by 2. So multiplying it with this one will actually become 3 by 2. So what is the final answer? The final answer becomes half m root mean square speed is equal to 3 by 2 kt. This is also one of the very famous equations of thermodynamics. Now let's try to discuss what this has become. This property is microscopic. Now what do we mean by microscopic? If I know the properties of one atom, I can describe the property or the temperature of the whole system, right? So for example, and this one is actually macroscopic. You see, K is a Boltzmann constant that does not change. So what has this equation actually come down to? 3 by 2 is also a constant. That the kinetic energy of the system is actually proportional to the temperature or the thermodynamic temperature of a gas. So if we know the properties, or property of just one atom, of the gas, I can talk about the temperature of the whole gas, even without checking that, even without checking with every atom, right? So we are going to do that proof over here. Whether does that matter or not? Be advised that most definitely, if we look at this formula, half mv square with this c square, right? So if we try with different gases, oxygen, nitrogen, carbon dioxide, and all the other gases in the atmosphere, the answers will be different. Why? The mass of oxygen and the nitrogen mass are different. So their velocities will be different. But after putting in these values in half mv square or half mc square, you will get the same answers. So that is what it comes down to. that the temperature will be defined by most definitely the mass and the speed square. Now let's try to do a simple proof. It can be found online as well that the average speed of an air molecule, oxygen, nitrogen, carbon dioxide included, ranges from 400 to 500 meters per second square at a temperature of approximately 27 degrees centigrade, right? Now we're going to do this proof to see whether we get the same answers or not. 27 degrees centigrade is actually 298 kelvins, right? Let's try that. I think it's 25. 25 plus 273 is 298, yes. So this is basically at 25 degrees centigrade, right? So these are mentioned in Kelvin, but most definitely they are representing 25 degrees centigrade of temperature. So temperature is same for both situations. Masses and velocities will be different. So the two gases that we're going to compare right now are going to be oxygen and carbon dioxide, I think. Yes. So we're comparing carbon dioxide and oxygen. So first, we start with oxygen's values. Oxygen is a diatomic gas, so this will be 16 multiplied by 2. So the mass of the oxygen atom is 32 U. Now what is U? U is an atomic mass unit which tells us what the proton and the neutrons actually weigh, what are their masses if they are inside the nucleus. So most definitely the number of protons and neutrons are 16 for one atom and 32 for all the atoms. So let's put in the values. So half mc square is equal to 3 by 2 kT. So 1 over 2, the mass of the gas is going to be 32 U. So 32 multiplied by 1.66 into 10 raised to power minus 27 into c square equals to 3 by 2. The Boltzmann constant is 1.38 power minus 23. So this will be 1.38 into 10 raised to power minus 23. Again multiplied with the temperature in Kelvin, which is 298. So be advised that this is a square. When you solve this completely, taking the under root over there, so the velocity actually comes out as, for oxygen, it comes out as 481 meters per second. So I'm going to put in the values over here that the first one is oxygen and the second one will be carbon dioxide. So the velocity over here comes out as 481. The mass was 32 U. And if you want to find out the kinetic energy, this will again, if you put in this value 481 meters per second into this equation, you will get an answer of 6.14 into 10 raised to power minus 21 joules. Now what we're trying to prove here is that if one of them has a higher velocity, its mass will automatically be less. But for the temperature of 298, which is over here, the kinetic energy will be the same across the board. Let's do this exactly the same exercise for carbon dioxide. So for carbon dioxide, this will be the mass or the molecular mass is 44 U. I'm going to put in the values directly because we have already discussed what is 32 U over here. So this will be 1 over 2, 44 into 1.66 power raised to power minus 27 multiplied by the root mean square speed equals to 3 by 2 and Boltzmann constant, which is 1.38 power minus 23 into the temperature, which is 298 for this one. So 298. You'll find out the mean root mean square speed to be a bit less because the mass is higher. So this comes out as 410 meters per second. 410 meters per second. Right, so let's fill in the value. So this is 410 meters per second and the mass was 44 U. But if you put in the values exactly in the half mv square formula, you will get 6.14 into 10 raised to power minus 21. As we can see from this calculation, from this exercise, that although the masses can be different, their velocities can be different, but their kinetic energies will be exactly the same for the same temperature. This is why we have always concluded that temperature and kinetic energies will be the same for ideal gases, if the gases are behaving ideally, right? So let's go back to the syllabus and see whether we've covered everything. So yes, we understand what is RMS speed. We have given this proof as well, and we understand how it is equal to 3 by 2 kT from this system. We understand how we got the 3 by 2 kT factor, right? Okay.